Mhm. Okay. Start the broadcast. If the you know, if the image doesn't work, just let me know. It was kind of on the fritz with the last group. Give me just one moment. One other thing. Okay. So we're gonna go ahead and get started, and I'll check Zoom again for anybody that's coming late around the 15-minute mark, like I usually do. Let me see. So one piece of information. This doesn't pertain to anybody on the call right now because everybody that I got onto the call, they were on my roster. But if you have a classmate or a friend that was dropped from the roster, they need to contact me and I can add them. We can get them added back. They would start by emailing me with their first and last name with their M number, and requesting to be added back to. They got to identify the class too. The simplest thing is having the correct M number with the CRN, and then you want to follow with the email. Like the best thing is just to come to class and say, "Hey, Mr. Pfeiffer, I think I got dropped. Can you add me back?" And then we can make sure to get you added back. But like I said, that doesn't pertain to anybody on the call right now because you all were on my roster. I'm just, encouraging you to look out for your classmates or your brother or whatever. Another thing is that we are rapidly approaching the end. Like we are in the home stretch, right? So let me pull up the calendar really quickly. So like as I glance at the calendar, we have this week, I think we have 2 weeks of new material remaining. So we have the material from today, we got some new material next week, and then the following week is November 21st. We're going to meet on that Monday. We're going to start to review for the final, right? So we're going to meet on that Monday, the 21st of November, but then the 23rd on that Wednesday, more than likely we won't meet because that's the Wednesday before Thanksgiving. So, take your Thanksgiving break and enjoy your holiday, spend time with your loved ones because, you only get one shot at that moment in time, and that moment in time does not come back around. So try to make the best of it as best you can. Then we come back for Thanksgiving and we meet. We have 2 more days. The last official day of class, I'm under the impression, is November 30th, which is that Wednesday after Thanksgiving. The reading period is usually that Friday, so that's December 1st and 2nd. And then the following week, we are in finals, right? So ours is going to be, you can anticipate it to be held similar to we've done all our exams. This is remote. So it'll be available online. It should become available that Sunday morning, the 4th at 11. I think I set them all for 11:11. But we're rapidly approaching that hard deadline of that Friday, December 9th, right? So if you're online, if your material online is not where you want it to be, now is the perfect time to just get that stuff in order, right? If you're trying to go back and improve old scores, my recommendation is to prioritize the exams because the exams count for nearly 80% of your overall grade. So that's where you're going to get the most bang for your buck. I would encourage you to take, you can work on them together, sit down with your tutors and work on it. It's going to be okay. But you just want to prioritize your exams. Now, if you have the gumption, if you feel up to it, you can go back and work on your old quizzes and quizzes and homework. but you want to prioritize the homework last because that's going to be the most work for practically no points, right? You're not going to see your grade move for doing a whole bunch of old homework, right? That's a lot of work for a little bit of points. If you're really trying to see movement in your grade, you want to go back and improve your exam scores. And we talked about the hard deadline. Yeah, and the exam should be available now. But the final, there's no late opportunity for the final. It's going to be available from that Sunday, December 4th, until that Friday, December 9th at 11:59 p.m. And so once we hit that that Friday, that's it for everything. Because then at that point, we have to calculate final grades and put things in order and submit them. So we can't go beyond that. So again, I just want to encourage everyone to go ahead and try to get that stuff in order like as soon as possible. Yeah, and then just to kind of reiterate, when this is remote asynchronous, and so what that means is that I still need everybody to, at a minimum, log in each day to get your daily attendance credit. We don't meet on Fridays. Now, that might be your lab, but that has nothing to do with me. That's going to be Dr. Lamar, or whatever you worked out with her. So, we only meet on Mondays and Wednesdays for this portion. And so I do need you guys to check in. It's important. And it basically, it's just administrative things. Administrators are like, when was the last time you saw so-and-so? Well, my records say that this was the last time I saw so-and-so. But I don't give grades. All I do on my end, I just write down what you guys are doing, and I try to encourage you to do what you need to do, so that you can get what you need. You can position yourself for success. That's all it is. I'm just trying to help you guys. I'm totally indifferent. It's no skin off my back. I just want to see you guys succeed, really. But I can't make you do what you need to do. I can only make myself available and try to encourage you. That's all I can do on my end. Okay. I can't think of anything else. Let me think. So this week, let's do this for now. This week we're working on, so this is the second, next week is the last of the new material. So today we're going to be working on section 3.1, exponential functions. A few objectives. We like to define an exponential function. We like to graph exponential functions, develop formulas for simple and compound interest, understand the number e. We want to graph the natural exponential function. We want to model with exponential functions. Okay. Actually, I want to do something a little bit different with you guys than what I did with my earlier group. I just want to kind of go through a story. Oh, it's doing this thing. Oh, I forget. It always freezes when I try to do that. Let me check here real quick. Give me just a moment. Barkity bark.
I have a question.
Yes.
How many questions gonna be on the final?
Oh, that is a good question. I have no idea.
Is it over just the new chapters that we learned, or is it over everything?
Everything. That's what I was about to say. It's cumulative. So it's a little bit from everything from the beginning. It's the same format, right? It's just everything from the beginning to end. So what that means is you take it. If you don't like the score, you could take it again, but it's going to change the same way exams 1, 2, and 3 did. But it's a little bit of everything from the beginning to the end. Let me see. What was it? Oh, I'm trying to fix this thing. Yeah, that's a good question, though. So I had to reboot it. We're here. Yeah, for some reason, it just throws a tantrum whenever I try to add a page. I don't know why it does that. Let me see if I can add this page first. Right here. Okay, and then this template. Just to be consistent like this, apply. All right. And we can go like this, I guess. Single. Okay. That's fine. All right, let's bring the image back. You guys are looking good. Share the screen. Start the broadcast. All right. So since we're talking about exponential functions, there's actually 2 stories. This is just a story, right? So there is the story of the man who invented chess, right? And so the way the story goes is that, there was this local inventor. He came up with this new game, and it was the game of chess. And so he presented it to the ruler, and the ruler enjoyed his invention in the game of chess. He was so pleased that the ruler agreed to pay him his weight in gold as a reward. But the inventor, he's like, well, he offered a different suggestion. He was like, okay, on the first tile of the chessboard, you could put 1 grain of wheat. On the second tile of the chessboard, you could put 2 grains of wheat. On the third, you could put 4, and then 8, and then 16, and keep doubling it each time until you get, fill each grain, each cell, each tile on the chessboard, right? So the king thought about it for a moment, and he said he agreed to it. So let's just see how many grains of wheat did the ruler agree to pay this inventor, right? Okay. So the chessboard has a total of like 64. I think it's 8x8, right? It's 8x8 tiles. So let's see. On the first tile, so we'll just call it N. He agreed to put 1 grain of wheat, and notice that 1 is the same as 2 to the power of 0, right? So I think this is going to be 2 to the power of n minus 1. All right. So then the total at that point is just 1 grain of wheat. Okay, grains, 1 grain. Now on the second tile, and let's change. We can say tiles, I guess. Okay. On the second tile, he agreed to put twice as much, 2 grains of wheat, right? Which is going to be basically 2 to the power of 2 minus 1, which is just 2, right? Let me think about this one. So then now the total is what? 1 plus 2, which is 3. Total grains is 3, which is going to be, here it is, 2 to the n minus 1, like this, right? So 2 squared, right, just 4 minus 1 gives us 3. Okay, and so this one is 2 to the power of n minus 1. Okay. I think that's how that goes, right? Let's check a few more tiles. So if we think about the third tile, he's going to double the previous. So now it's going to be 4 grains of wheat, which should be 2 squared, right? And the total is now, 3 plus 4? It should be 7, which should be 2 cubed minus 1, 8 minus 1, right? Let's do one more. Let's do a couple more. The fourth one, right? So that's going to be 16, which is 2 cubed. Nope, not 16. It's going to be 8. Okay. And then the total, 14, 15, it should be 15, which is going to be 2 to the 4 minus 1, right? So then now the question is, how many grains of wheat did the local ruler agree to pay, right? So the chessboard has a total of 64 tiles. So on the 64th tile, it should be what? 2 to the power of 63 grains of wheat just on that one tile. And then the total is going to be 2 to the power of 64 minus 1. All right, grains. This number ends up being something like 15 quadrillion. It's a huge number. I'm going to try it. Hey Siri, what's 2 to the power of 64 minus 1?
2 to the 64th power minus 1 is approximately 1.8446 times 10 to the 19th power.
6 times 10 to the 19th power, right? So let me see. So that's a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. I think that's how that goes. Let me check. 1, 2, 1, 2. I think this is it, right? And so if we count this, let me see. This is thousands, millions, billion, trillion, quadrillion, 18 quintillion grains of wheat, right? That's much more than his weight in gold. 18 quint, that amount, I forget the dimensions that would fit inside of, but it was something like, I think it was like 25 miles by 25 miles by 1,000 feet high silos, some huge silos, something like that. That was much more wheat that has ever existed in the world, even into this day. So he kind of like tricked the ruler into like giving up everything. When the ruler realized that he couldn't pay this guy, the story actually kind of has a dark ending. At least this is how it was told to me. Supposedly, when the ruler realized he got tricked, he was like, off with his head. So, but what this is just interesting, right? It's just an interesting story, right? But what this is a demo on how quickly things can grow when you start behaving exponential in nature, right? Like our bank accounts are about to do, right? If that's going to make a difference. I don't even know if the fiat dollar is going to survive. And like, I don't know. I feel like something big is about to shift, but I don't know what it is. But in the meantime, right? You know, and having money, I don't even know. If you don't love yourself, no amount of money is going to make a difference. You got to love yourself first. That's just how I feel about it. You know, you can get distractions, but I feel like a bunch of money, if you don't love yourself, then you're just going to find more things to like. It's just going to make things worse, in my opinion. But that's neither here nor there, right? So that's the story of this inventor, the invention of chess, you know, and how that story goes. Okay. So that was a demo on exponential growth and how things can grow exponentially, and just a little bit of a demo there. And so we want to introduce this concept. Let me check Zoom really quickly. Okay, let me log the student. Cool, we got him, coach. Okay. So let's get into, so this is like basically, you know, some of the details of the characteristics or properties of exponential functions, and what do we mean by an exponential function. So a function f of this form, where a is positive and not equal to 1, is called an exponential function with base a and exponent x, and the domain is all reals, right? So in the past, we were working with what's called power functions, where we had x to some power, like x squared, x cubed, you know, x to some power like that, right? So now we're flipping those. Now we're going to do things like 2 to the power of x. We're putting the variable in the exponent. So that's what makes this an exponential function. But one thing is that the base of the exponent has to be strictly positive and it is not equal to 1. Right? So as long as the base is strictly positive and not equal to 1, your variable's in the exponent, then it's going to behave like an exponential function. And the general shape of an exponential, on the far left, it starts off really, really close to the x-axis. It passes through the point 0, 1, and then it just grows exponentially like that. Let's see. This is the general shape of an exponential, all right? Okay. All right, so let's keep going. So here we're asked to, let me see, we're basically evaluating exponential functions. So for instance, for the first one, we're asked to let x be 4. Okay, so let's go here. So if we let x be 4, then f of 4 ends up being 3 to the power of 4 minus 2, which is 9. Okay. Copy. Okay. Let's do the next one. When x is negative 2. So then g of negative 2 ends up being negative 2 times 10 to the power of negative 2. A negative exponent means it goes to the denominator. It flips the fraction, right? So it becomes 1 over 10 squared. So that's really negative 2 over 100, which is like, I'm going to just leave it as 1 over, or if you're dividing here, if you're dividing by 100, you move the decimal to the left twice. So 0.02. Okay. So then next is let x be a negative 3/2. So we have this h of a negative 3/2. That's going to be 1/9 to the power of a negative 3/2. So again, a negative exponent causes the fraction to flip. So this is really 9 to the power of 3/2. So a rational number, a rational exponent, what that is really a radical, like square root, cube root, right? So the denominator of the rational exponent is the index for your radicand, square root. If we were dividing by 5, we'll rewrite this in the following manner. This is going to be the same as the square root of 9 quantity cubed. Square root of 9 is 3. 3 to the power of 3 is 27. Okay. So a rational exponent is really a radical, and a negative exponent flips the fraction. Okay. And then for this last one, I would just encourage you to use your calculator. Just use your calculator for something like that. Okay. See, we got our 9. You see all the results here. And then from the calculator. Okay. And I'm just going to kind of use the notes here for this one. So we're asked to graph this exponential function. We have 3 to the power of x. So if I were doing something like this from scratch, I would just choose these values of x. So just myself, I would just say, okay, let x be -3, -2. You choose these values, and then you just find the corresponding y. So we're basically plotting points, choosing values of x, finding the corresponding y, plotting the ordered pairs. So if you put these ordered pairs on a graph, you'll get this, something like this. And then you connect those ordered pairs with a smooth curve, and we finish with this image on the right. So notice that the domain is all reals, right? Every x is accounted for, right? There's no matter what value of x, you can find the corresponding y. Going off to the far left, we get infinitesimally close to the x-axis. The exponential function lies entirely above the x-axis as long as it hasn't been manipulated, right? So the x-axis serves as this concept called a horizontal asymptote. What that means is that in the long term, we get infinitesimally close. It looks like it's going to be touching, but if you actually zoom in, you'll find there's always space between our function and that asymptote, right? So the asymptotes tell us about long-term behavior. And then in this case, going off to the right, we grow exponentially, but there's no vertical asymptote. There's only the horizontal one. Okay, hopefully that makes sense. So we saw an example in the previous example where the base was larger than 1. Now we're going to look at where graph an exponential function where the base is between 0 and 1. Okay, so just like before, we would choose values of x, find the corresponding y, and plot the ordered pairs, right? Remember, a negative exponent flips the fraction. So this, when x is -3, it's really 2 to the power of 3, we get 8. 2 to the power of 2 is 4, yada, yada, yada. Okay. All right. Okay, so we chose the x values, found the corresponding y's, and then we plot the points and we get an image like this. So this is what we call exponential decay, right? What we saw before, we had exponential growth, whereas we trace it left to right, the graph increased, it just kept increasing. But now as we trace it left to right, it's decreasing, it's steadily decreasing. Okay, but this is called exponential decay. Okay. So we have some properties of exponential functions. So let f of x, let me see the time. Let f of x equal a to the power of x, where the base is strictly positive and not equal to 1. The domain of an exponential function is all reals. The range of an exponential function is 0 to infinity, the open interval 0 to infinity. And again, parentheses in this context means we get infinitesimally close to 0, but we don't actually reach it. So, you'll get really, really close. You have a whole bunch of points that get infinitesimally close, but there's always space between our function and 0 as long as we don't manipulate it. Okay, the entire graph lies above the x-axis. Okay, so there's no x-intercept. There's a y-intercept, but no x-intercept. So since f of the x plus first term divided by f of x is going to be a to the power of x plus 1 over a, but then the top can be rewritten as a to the x times a. And then if you cancel like terms, we finish with just a. So then what this is telling us is that the y value changed by a factor of a for each unit increase in x, right? So every time x increases by 1, y increases by a factor of a, whatever the base of our exponent is, okay? When the base of our exponent is strictly larger than 1, that's called the growth factor, is going to be a. Because the y value is increased by a factor of a for each unit increase in x, f is going to be an increasing function, so the graph rises as we trace it left to right. As x goes off to the far right, y goes to positive infinity. As x goes off to the far left, y tends to 0. Okay, so that's what we saw with that horizontal asymptote. So then when the base is between 0 and 1, we call this the decay factor is going to be a. Because the y value is decreased by a factor of a, by a factor of a for each unit increase in x. That's where we had the exponential decay. So f is a decreasing function, so the graph falls as we trace it from the left to right. As x goes off to the far left, y goes to positive infinity. As x goes to the far right, y tends to 0. Each exponential function is 1-to-1, right? So what that means, 1-to-1 means that every y corresponds to exactly 1x. You don't have the case where one y corresponds to more than 1x. An example of something where it's a function, but it's not 1-to-1 is going to be the parabola, a U-shaped curve. This is a function because it passes the vertical line test, but we can find a y. Lost it. Let's do it another one. So we could find a y value that corresponds to 2 different x values. 1x, and the other one will be here, right? So we have one y that corresponds to two x's. This would be a function. It passes the vertical line test, but it is not 1-to-1, meaning you have one y that corresponds to more than 1x. So whenever you hear me saying 1-to-1, that's the same as saying the function has an inverse. That's the same as saying every y corresponds to exactly 1x. That's the same as saying it passes the horizontal line test, right? And then algebraically, to show a function is 1-to-1, if you start with if you equate 2 different y values, then that means that the x values have to be the same. If this technique falls, then it's not 1-to-1, right? So 1-to-1, having an inverse, passing the horizontal line test, and every y corresponds to exactly 1x, those are all saying the same thing, just 4 different ways. Okay, I know it's a bit much, but yeah, that's what it is. The graph of f has no x-intercepts, right? So if we think about an exponential function, remember the exponential function, the graph lies entirely above the x-axis, so it'll never cross the x-axis. No value of x will cause the exponential function to equal 0. The graph of f is a smooth, continuous curve, and it passes through these 3 key points. So namely, when x is -1, when x is 0, and when x is 1. When you find those 3 order pairs, that gives you the general shape. You can tell if it's exponential growth or exponential decay rapidly from these 3 key points. That's where the main shift changes. From 4-3 and 5-3, we conclude that the x-axis is a horizontal asymptote for every exponential function of this form, right? Without manipulations, the x-axis serves as a horizontal asymptote. That means in the long-term behavior, we get close to it, going up to the far left. The graph of y equals a to the -x is the reflection about the y-axis. We have a -x on the inside of our basic function, so it's going to cause it to flip horizontally from our transformations. This is basically just where we had the exponential decay, right? That's all that is. All right. I have this urge to share another story, all right? Just to kind of break up some of the monotony. And I think it still holds to this day. I haven't been able to create it yet, but I think it actually still holds. So there's this story, let me see. well, it's not a story, it's something I witnessed. But the concept is called, it's a concept called the infinite scholarship, right? And so what it is, basically, when I was a student at Morehouse, I was going to like an honor society meeting, and they were describing a fundraiser that they had going, and they called the fundraiser the Infinite Scholarship. And so what it was their efforts to earn or generate or raise funds up to about $1 million, right? But it had an interest-bearing account that at that time the rate was like maybe 5%, simple interest, the lowest form of interest, right? So they had an interest-bearing account that had $1 million. They were trying to put $1 million into this account that earned 5% every year. If you do a quick calculation for 5% of $1 million, here, let's do it here. Hey Siri, what's 5% of 1 million?
5% times 1 million is 50,000.
So what that is, if you have an interest-bearing account earning 5% interest, and the principal is $1 million, that ends up to be $50,000 a year. That's actually a full-time check. That ends up being almost like a couple of $1,000s a month, right? So that's honestly one of my goals. I've been aware about this the whole time. I just haven't obviously gotten, that principle. But I know people that have had that kind of money and they weren't aware of this. So when you get your $1 million, when you get a large lump sum of money like that, and you can find an interest-bearing account earning at least 5%, then that's basically like a couple of $1,000s a month, right? And so like as long as you don't touch the principal and you only live off the interest, then that's generational wealth. You'll have at least $2,000 coming to you as long as that account is active. So you don't have to punch a clock, you don't have to do anything. You just collect the money and go live your life. That's the kind of stuff that I personally am trying to build, not only for myself, but for as many people as possible. I know that we had like athletes that graduated with me. I know people that have this kind of money. I just don't know if they're aware of like these dynamics, right? But at least if you're aware when you do get it, you can create it. And as long as you don't touch the principal, you'll have at least $2,000 a month coming in, and you can always go bigger. You can make it bigger. So that was the goal of this thing called the Infinite Scholarship. And so with that account, as long as you only don't spend more than the interest, you'll have money forever. That's just one of them. I mean, that's some of the things that I study. Like another example of something like this. So now we're kind of talking about like passive income. Now, I don't really believe that there's a thing that's truly passive, but there are a lot of things that fringe on it. And I'm no financial analyst, no guru or anything. You would have to sit down with a financial analyst to, get more details. But like some other things that kind of behave in that manner are like real estate, or like if you there's a person in one of my groups that's like his father left them this real estate property that earns $20,000 a month. There's a property manager that manages the property. They interview tenants, they review applications, they get tenants in there, they make sure that they pay. If they don't pay, they get them out, get somebody else in there. There are people that's what they do. And so as the owner of this property, him and his sister just collect $20,000 a month, and they, squabble over that, but they don't have to do anything else. Like that's what I'm trying to leave for as many people as I can, because I personally don't believe in like trading time for money. There's a lot of people that do, most people do, but that's the lowest way to make money. We all have the same 24 hours in a day, right? But some people like, what is it that other people are doing different with their 24 hours than the average mojo or whatever, right? But real estate, and then another one is called dividend stocks. There are companies that will pay you a percentage of their profits every year just for owning stocks with them. So there are people that like have a bulk of money with these companies, and every month they get like a sizable check just for having money with them. It's not really a bribe. It's just like the company saying, "Hey, thank you for doing business with us, and here's a portion." They basically divvy up like the profits each year, and they give it to their stockholders, right? I mean, it's all over YouTube. Like these are the concepts that I research and I study amongst like trading, cryptocurrency, forex trading, and it was actually one of my former students that got me into it. I haven't done anything with it yet. It's just something I'm working on my own. But yeah, so these are things that I know I've eaten up all the time. You already have a recording of all of this stuff, so that's why I don't mind going into these rants, because whatever we don't do here, there's there's a full recorded lecture for this kind of stuff. But I felt like I just wanted to kind of get this to somebody's attention that maybe you can take some of this information and like build it and transform your life. But yeah, so those are just some of the things: the infinite scholarship, dividend stocks, compound interest, real estate. If you set it up properly, it can be residual in nature. It takes work, but it's possible. It's possible, right? So that's the long and short. We got a solid 5 minutes, so we're going to go ahead and use that 5 minutes and kind of get back on track. But I personally enjoy the stories. Again, I don't mind doing it because we have a recording of this stuff, the whole thing already, right? And we only get 50 minutes, so that's why I made that stuff in advance. So then we have some definitions. We have the interest rate is the percent charged for the use of the principal for the given period, right? So the interest rate denoted by R is expressed as a decimal. Unless stated otherwise, the period is assumed to be 1 year. That is, R is an annual rate. The amount of interest computed only on the principal is called simple interest. So simple interest is the lowest form of interest that we have. You're going to see in the next slide, that's going to be I equals PRT. And let's just take a look at it. So if you have your formula sheet, this is a good one to just add simple interest. Again, this is the lowest form of interest. Okay, I equals PRT. So in this example, Juanita has deposited $8,000 into a bank for 5 years. A simple interest rate of 6%. How much interest will she receive, and how much money will be in her account at the end of the 5 years, right? So it's a good idea. Again, it says simple interest, so it's a good idea to use the simple interest formula. I equals PRT, okay? How much interest will she receive? So then for part A, the interest earned is going to be the principal, which is 8,000, times the rate, which is 6% as a decimal is 0.06, okay? So whenever you're doing the rate, you have to convert it to a decimal. And the unit for time is usually in years. So you got to make sure that's in years. It says for 5 years, and you just multiply. What is that, a 3? Normally it would be a 30.03. Hey Siri, what's 8,000 times 0.06 times 5?
8,000 times 0.06 times 5 is 2,400.
Okay. So what that means, and I know that's not impressive as far as the amount, but it is impressive as to how it was earned. She didn't have to do anything for it. And again, if you think bigger, if you get bigger sums in that account, then your return will be bigger, right? We kind of discussed the whole compound interest and all that. And then for part B, how much money is going to be in our account at the end of the 5 years? So then if we want the future amount, that's going to be her starting amount plus the interest earned. That's going to be the $8,000 plus the 2,400. Give her 10,400. Right. So like this could be like, your children's like college fund or something like that, or a trust or something that you want to like leave to somebody when they come of age and like they kind of, and like at some point we have to start thinking like beyond ourselves, like, do what you can for yourself, but then obviously we don't stay in these bodies forever. So you're gonna leave something, whether you do it intentionally or not. So then it's like, okay, you want to start thinking, well, how can I impact somebody else's life? You know what I mean? Anyway, and there's totally an extra zero on there. I always get sleepy around this time. Okay. I think we're gonna wrap up here. I do want to talk about compound interest. Compound interest is the interest paid on both the principal and the accrued interest, okay? This isn't our compound interest. This is like if the interest is applied once in a year. I want to go to the next one. I'm going to leave this one as an exercise. And I want to talk about this one. So this is the one that we use more often, which is the compound interest formula. This is when you have multiple compoundings per year, where A is the amount after T years, P is your starting amount or the principal, R is the rate expressed as the decimal, it's the interest rate. N is the number of compoundings per year. So how many times the interest is applied in a year. and then t is the number of years. And so for this example, I'm going to leave this as an exercise for you, but I want to prime it. I want to like just kind of give you the main thing that you need. So it says $100 is a deposit into an account that pays 5% annual interest. Find the future value A after 1 year if the interest is compounded for these different compoundings, right? So the only thing I want to add for right now, the first one is if n were 1, if it's compounded annually. Semi-annually be n equals 2. Quarterly is n equals 4. Monthly is n equals 12, and daily would be n equals 365, right? And you would apply these to the previous formula and, go from there. Okay? And there's more, but again, I'm going to have to encourage you to watch my pre-recorded lectures on this to get the full thing, and then, make your way through the assignments. Are there any questions for me? Any questions? Once, twice. Okay, so if there aren't any burning questions, let me go ahead and make a copy of this available for you. So phone, I got 1, this one, notes, week 13. Yeah, we're good, okay. So when this bar finishes loading, you'll get a copy of anything that you saw me writing. And if there aren't any burning questions, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day, guys. Take care. Peace.